So today we would like to introduce the notion of the complex plane system to represent complex numbers, which we introduced in the last series, or the last video. If you're returning from the last video, I hope you found it captivating enough to continue today. Anywho, we would like to describe the complex number system by using the imaginary part of a complex number and the real part of a complex number, which we introduced at the end of the last video. Of course, the idea of a complex plane is that complex numbers come in the form that z is equal to a plus ib. And of course, we label the real part of z as being a and the real part, the imaginary part of z as being the imaginary coefficient b. Of course, these represent the different coefficients. So as you could tell, you can represent the complex number z graphically. Say that this is your point A and this is your point B. You can represent this as a point on the complex plane. Now, I hope you can see where this is going in future units. The functions defined by complex variables will be two variable functions of the real part and the imaginary part, and they will define a plane. Anyways, what we'd like to do today is to tinker around with the idea of finding distances on these planes, which we will get into now. As you should see with some elementary algebra, it is not too complicated to deal with. We'll start off with a definition for the distance, such that the modulus, which is a new name that we have, of the complex number z equals a plus bi is denoted by z with absolute value bars around it. And this quantity is defined to be the sum of the squares of the components. This is a direct consequence of the Pythagorean theorem using the complex plane system. Okay, so if you can tell, if I had a plane system and I had a coordinate a and a coordinate b, then obviously the distance between those 2 points, or the distance between the origin and those points, would be the hypotenuse of that right-handed triangle that we created. So to do that, you take the sum of the squares of the two components, a squared plus b squared. The good news is, unlike in multivariable calculus, this does not get any more complicated. So again, I would consider the complex plane such that any ordered pair AB, the coefficients representing the complex number, are mapped to some point on the xy plane. So essentially what we're doing is we're taking the complex numbers and we're mapping them to the two-dimensional real number plane, and that is denoted by r superscript 2. Now, if we have defined the magnitude of a complex, the modulus of a complex number, to be the sum of squares and its square root, then it better be positive. The square root of a sum of squares is positive, and it also belongs to the real numbers. The modulus will not belong to the complex numbers. You also consider taking the distance between two different complex numbers, z sub 1 and z sub 2. Well, of course, what you will use is you will use the generic distance formula, again, an extension of the Pythagorean theorem that we can use fairly easily. Finally, I thought I would throw this in as a brief remark. If you would like to find a circle that is sweeped out, you can define a distance between some variable number z and some number z naught, but you fix that distance to r, such that any number between z, or any point satisfying this equation, must lie in a circle around the complex number. So you can define a circle using that modulus definition. Anyways, we can move on to an example. This example is from Saff and Snyder. This is the book we will be following closely. From section 1.2, this is example number 2. And they're asking us to describe the set of all points which satisfy two different relations. So the first relation is z plus 2 modulus is equal to z minus 1 modulus. And then they want us to also consider the set of points where the modulus of z minus 1 is equal to the real part of z plus 1. So this bit looks a bit complicated to us, but I promise it is fairly trivial to actually conduct. Anyways, the general thing that you want to do here is if you see z, you'll replace that with x plus iy or a plus ib. I prefer to use x plus iy because we want to look at a series of points in the xy coordinate plane. So anyways, what we'll do is we will take this first equation, replace z with x plus iy, and evaluate the modulus. So what we do is we plug this into a square root. Of course, the real part of the number z equals x plus iy plus 2 is going to be x plus 2. So that's the real part. We square that. Then we take the imaginary part, which is just y, and then we square that. And then we do the same thing for the right-hand side, such that we have the square root of x minus 1 squared plus y squared. So what you can do now is take the square of both sides and FOIL out all of the remaining equations, and you get the relation that x squared plus 4x plus 4 is equal to x squared minus 2x plus 1. And this implies that x is equal to negative 1/2. So as long as the line is on the as long as the line lies within x equals negative 1/2, if that defines a series of points, then the equation is satisfied. So essentially what this is saying is y is pretty much held as just a given. It's just a variable here. The only thing that's being modified is the real part, which is x, because we're shifting it by negative 2 and then positive 1. So essentially what this is doing is this is taking any line, any horizontal line between x equals negative 2 and x equals 1, and it wants to find the line, it wants to find the point where in between the line x equals negative 2 and the line x equals 1. So the perpendicular bisector of the line between x equals negative 2 and x equals 1 is the line x equals 1/2. So that's the equation that we get for this solution. Anyways, we can move on to the solution for the second part, which is a slightly more complicated affair. But we start off from the same principle by substituting in x plus iy for z, and then taking the real part and pushing it over with x, the real part of z. So we get the square root of x minus 1 quantity squared plus y squared is equal to x minus 1. Now, there's a little bit of funny business going in here. If I take the real part of z, if I define z to be x plus iy, then the real part of z is going to be x. So just get x, and then this should, in theory, be a plus 1, actually. So I've made a slight typesetting error. That should be plus 1. And what we have now is something that we need to FOIL and expand so that we can solve it analytically as an algebraic equation. So we get x squared minus 2x plus 1 plus y squared equals x squared plus 2x plus 1. And simplifying this all out, we get y squared equals 4x, which is the equation of a parabola. Okay, I'd prefer not to draw that one out, but I can draw out the original one for part A being kind of the line between, if this is x equals negative 2, this is x equals 1, well then the solution point is going to be right here at x equals negative 1/2, since the distance from here to here is the same from the distance from there to there. That was a bit incongruent, my drawing, but it doesn't matter in the end. In the next video, we want to continue looking at the idea of the complex plane by introducing the idea of the conjugate of a complex number. We'll look at the conjugate, we'll look at the properties of the conjugate, we'll play around with some examples. So I hope that sounds good. And then just in the future, we'll be considering the polar form, the exponential functions, the roots of unity, and finally, planar sets. Thank you for watching today's video. We'll be back for video 3 to discuss the conjugate of a complex number. See you then.